At the end of lecture 13, we derived an expression for how the temperature changes as you move along the volume of a jacketed plug flow reactor. And that equation was dt dV equals RA times delta H, which is a function of temperature, plus UA times the jacket temperature minus the temperature at that point in the reactor, divided by the sum of CPI times FI. And what I would like to do today is to solve an example where we have to implement this. And of course, if we're going to do that, we need a problem to solve. So let's look at one. And we're going to consider the gas phase reaction A plus B goes to C in a jacketed PFR. We know that A and B are fed to the reactor as an equal molar mixture with a total flow rate of 5.4 moles per second at 120 degrees C and 20 bar. We're going to plot the molar flow rates of A, B, and C, as well as the concentration of A, B, and C, and the conversion as a function of the reactor volume. And we're going to determine the reactor volume to achieve a conversion of 0.8. So we also know the pre-exponential factor for our rate constant. We know the activation energy for the reaction. We have an empirical relationship for delta H of reaction as a function of temperature. We know the jacket temperature and the heat capacity of all the species and the heat transfer coefficient. And so we can use all of those to solve the problem, okay? So what we're gonna need to do here is to have both the energy balance and the mass balance for each of our species. Now we know for a plug flow reactor that our mass balance is dFi dV equals Ri. And if we implement that specifically for, let's say, A, well, we know that that's equal to Ra. And the rate law when A plus B goes to C, if it's an elementary reaction, is minus K1 times Ca times Cb, right? So we'll say A plus B goes to C, and we'll assume that this is elementary. Okay. And we can just as easily write rate laws. dFb dV equals minus K1 times CaCb for component B. And by stoichiometry, dFc dV equals K1 times Ca times Cb. Now, a lot of times what we would do previously in this semester is solve examples where now we want to get everything either in terms of the concentrations, right, and make a substitution here for Fa, or what we'd like to do is to get everything in terms of conversion, right, and we would substitute for conversion here, here, and here, as well as there, and get larger, somewhat more complicated expressions, which of course we know we're going to have to solve this problem computationally anyway, just as we discussed in lecture 13. Now, if that's the case, we don't always have to exactly move towards making those substitutions. In fact, what I'm going to try to show you here is how we can keep the mass balances very, very simple and implement them directly in Excel using Euler's method. And what we'll do is we'll make cells to independently calculate the things that we are interested in. Like, for example, we know that the concentration of any of these species is just the flow rate of that species divided by the volumetric flow rate. And at any point along the length, we also can calculate the volumetric flow rate, because that's equal to V0 times 1 plus epsilon x times P0 over P times T over T0. Now, of course, in this example, we're assuming that it's isobaric, so we don't have to worry about that at all. And we only have to worry about the temperature in this particular case, okay? We also know that we can calculate the conversion when we know the flow rates, because the conversion of the reaction is related to the flow rate of A, right? We know that Fa equals Fa0 times 1 minus x. So at any point here, we can actually solve for the conversion based on the molar flow rates. And that'll be very, very helpful to us, because if we need the volumetric flow rate, right, to calculate the concentrations, we can just implement that here. So I'm going to leave these mole balances alone, and we're going to implement them in Excel exactly like this. So then the only thing that we have left to do really is to take this expression and to think about the changes that we're going to make based on the information here in the problem. Okay, so to do that, I'm going to try to give us a little bit of space, and I'm going to move this down to here. And if we're going to start with dT/dV equals RA times delta H of reaction, which is a function of temperature, plus UA times T star minus T over the sum of the heat capacities over the flow rates, well, we can easily make two substitutions here, right? So dT/dV then equals, and we know RA, of course, is minus K1 times CA times CB, then of course multiplied by delta H of reaction, which is a function of temperature, plus UA times T star minus T, divided by the sum of CPI FI. Now we know in this problem, we have 7/2 R for the heat capacity for all species. So this just becomes CPI times the sum of the flow rates. And so this becomes FA plus FB plus FC. And this is exactly how we're going to implement it in Excel as our fourth equation. So we have four unknowns, the flow rates of each of the species and temperature, and everything else we're going to calculate from there. So we have four equations and four unknowns. The one thing that I want to point out though, before we do that and move forward, is to be very careful when you're solving problems like this with units. And I'll just give you an example here, that if we look at the unit for K1 that is given here in the problem. So K1 has a unit of liters per mole minutes. Okay, so we're going to look at this, right, as liter per mole minute. And the concentrations here are going to be moles per liter, and then times joules per mole, right, for delta H of reaction. So if we look at this, right, moles cancel here, and we end up with joules per liter minute. Okay, so that's one unit that we have here. Now let's take UA. So we're given the unit of UA, looking back at the problem, in watts per liter times Kelvin, right? So watts liter times Kelvin, and then of course we're going to multiply by temperature in Kelvin. So then the Kelvins are going to cancel, and we're going to get the units joules per seconds times liters. And so you'll notice, right, those don't match. The other thing we have to be careful about from a unit perspective is that the denominator has the proper units, because remember, this has to be in Kelvin per liter at the end. And so we of course know that R here is in joules per mole Kelvin times moles per second, right? So the moles are going to cancel. And so we end up getting joules per second liters. And of course, that's good that the joules are going to cancel. But again, we're in seconds here, minutes there. So that's just something I want to stress when you go ahead and implement this problem, that you make sure that all of the units match. Now, how are we going to implement these four equations as Euler's method? Well, here, this becomes relatively straightforward, right? According to Euler's method, we're essentially going to look at the size of a change in volume that still gives representative behavior, right? And so when we use Euler's method, we estimate delta T over delta V then is equal to this minus K1 times CA CB times delta H at that temperature, plus UA times T star minus T divided by 7/2 R times FA plus FB plus FC, or that delta T, which is of course the new temperature minus the temperature you're at that moment, is just delta V times all of this in brackets. And I'll cheat here just a little bit. Okay. And so that's how we end up implementing the energy balance. Now, the mole balances are even more straightforward because we're going to do the same thing here, except to get delta Fi over delta V. And we're just going to multiply by delta V on both sides. And so we know then that delta Fa just equals delta V times minus K1 times Ca times Cb. We know that delta Fb equals then delta V times minus K1 times Ca times Cb. And delta Fc equals delta V times times plus K1 times Ca times Cb. I almost made a little mistake there. And at first glance, this might appear to be a little bit uncomfortable for you guys because it doesn't look like that things quite match. But one of the things that you're going to see is that when we implement this in Excel for Euler's method, I'm just going to have independent cells that calculate K1, that calculate delta H of reaction, that calculate the volumetric flow rate, and then the concentrations of A, B, and C in our Excel file, and I will just call them directly when I do that. And so let's have a look here at the Excel file. And just like all of the other Excel files that I have, I try to organize things based on values that are given versus values you have to calculate. And so at the very top, you can see everything that was given in the problem is there. So we have the heat transfer coefficient in the units it was given. We have the temperature of the jacket in Kelvin. We have our equation to calculate delta H of reaction at a given temperature. We have our pre-exponential factor and activation energy for our reaction. We have our initial temperature. We have the pressure. We have the initial number of moles. We have the initial flow rate of B as well. We have Cp over R, we were given was 7/2 or 3.5. And then here's some values that we have to calculate based on the information that's given. So one of them is in calculating the volumetric flow rate, you need to find both the initial volumetric flow rate as well as epsilon. So let's do that here, just so you guys get to the same point that I am here. And to calculate the volumetric flow rate, we actually can use the flow version of the ideal gas law. And we know that PV divided by the initial pressure and the initial volumetric flow rate is just equal to F times R times T divided by the initial flow rate times R times the initial temperature. And here what we're after is just a way to find V0. That was really stupid. And to calculate the value for the initial volumetric flow rate, we're just going to use the flow version of the ideal gas law. So we know that P0 times V0 equals F0 times R times T0. And of course, then V0 just equals F0 R T0 divided by P0. And these are all given in the problem. So F0 is 5.4 moles per second. R is 0.08314 liter bar per mole Kelvin. We know T0 is 393.15 Kelvin. And we know that the initial pressure is equal to 20 bar. And from there, we can actually find the value of V0, which you can verify here in the Excel file is 8.83 liters per second. Now, the next thing that we can do is to calculate the value for epsilon. So remember, epsilon is just equal to the mole fraction of A times the change in the number of moles in the reaction divided by the absolute value of the stoichiometric coefficient for A in the reaction. So of course, this is just 0.5. We're told it was equimolar A and B. Delta N is -1, right? A plus B goes to C, and this is 1. So epsilon is minus 0.5. And of course, that's something that we also saw in the Excel file previous. So now, the last thing that we need to do is to calculate the initial concentrations of A and B, since everything else that we have is in terms of moles per liter. Now, to do that, we start again with the ideal gas law, right? In that P0, V0 equals F times R T0. And if we just multiply both sides by a mole fraction, we get that Yi times P0 times V0 equals the concentration of I at the beginning times R times T0, or the concentration of our species is equal to Yi times P0 V0 divided by R T0. And of course, we have all of these values, and Yi is the same for both A and B. So CA0 equals CB0, and we can see in our Excel file here that that is 0.3 moles per liter. Okay, and so now we've calculated the other 4 parameters. And now what you can see then is how I've implemented all of these to execute Euler's method in this problem. Now, when I do this for Euler's method, especially with PFR problems, the very first cell that I have after the steps in the volume is the temperature. And the reason I do that is just, for me, it makes logical sense that first we calculate the temperature. You're going to use that temperature then to calculate K1 right here. You're going to calculate delta H of reaction. Okay. And then we can, in each one of these columns, then we have FA, FB, and FC. Here's the volumetric flow rate, of course, using the equation that we already showed before, which is just V0 times 1 plus epsilon x plus the ratio of the temperatures. We calculate the concentration of A as just the flow rate of A divided by the volumetric flow rate, and the same thing with B and C. And then lastly, the conversion, you can see, is just equal to essentially 1 minus FA over FA0, or FA0 minus FA over FA0 here. And so those are all the parameters that we were after in solving this problem. And here's how it's implemented. And when you try to reproduce this problem later on your own, here's a set of values that you can rely on and know that you're doing this implementation correctly. So let's actually answer the problem here. Now, the first thing that is asked for is the molar flow rates. And so here they are, right? The flow rates of A and B, it's equimolar. They have the same initial starting concentration and flow rate, so there's no surprise that they perfectly overlap here. And then, of course, we have the concentration of C as well that is constantly increasing. Okay. The next thing that we wanted to look at was the reactor temperature. And what happens here is that we start at an initial temperature that is about, if we look here, right, it was 393 K. So it's approximately 400 degrees, which you can see there. And what happens is that right at the inlet, you have the highest concentration of A, you have the highest concentration of B, you have an exothermic reaction. So the temperature is going to go up and up and up. And the reaction rate, in fact, I plotted that as well, even though it wasn't specifically asked for, is the highest right at the beginning. So what happens is you're giving up a bunch of heat, and you're generating heat so fast that the jacket itself can't keep up with the heat transfer. And so the temperature actually spikes above the jacket temperature here and reaches about 670 Kelvin. And then what happens is that as the reaction rate decreases, you start consuming species, for example, the reaction rate comes down, and then the jacket is able to remove heat faster than it's being generated. So the temperature here actually dips a little bit, and eventually over the reactor length, you get to simply the jacket temperature. And it's as soon as the heat transfer rate can keep up with or exceed the reaction rate here. And so what you see here is there's a bunch of reaction here at the beginning, or at least the reaction rate is very fast at the beginning. And then you can see that, there's a spike also in the volumetric flow rate, right? The temperature spikes, and we're losing moles here in this reaction. And then those end up balancing to end up with a volumetric flow rate that's very, very similar to where we started. And now if we look at the conversion, right at the inlet, we can see that the conversion actually goes up relatively quickly, right? It comes up over the first couple of 100 liters, and then it starts to level off once we get to 1,000 liters. Now, in this problem, we weren't just asked to plot the conversion. We were actually asked to find the conversion or the volume that's needed to achieve a conversion equal to 0.8. And if you look at this, we can get it off the Excel file. We can read it directly off the plot, but that's 469 liters. Okay. And so hopefully this problem has helped you guys to understand a little bit about how we can implement the mole balances as flows, not just as concentrations or conversion as we've done in the past. And hopefully that helps. And then how also we can implement the energy balance for a jacketed PFR, which of course we're going to need software for just based on the complexity here. Okay. Now, the other questions that are interesting to answer. So once you go ahead and you set up the Excel spreadsheet that I showed, there are some really interesting questions that you could start to explore and to answer on your own. And the first one is, how do the process variables affect the reactor conditions, right? Or how can you change the reactor conditions and then observe how the concentrations, the conversion, the temperature, and so on are changed? And we could change the preheating temperature of A and B, right? Or the initial temperature. We could change the rate constants. We could change the pressure. We could change the heat transfer coefficient. Where you could imagine, for example, if you were to reduce the heat transfer coefficient, that the spike would be even larger than it was here. And maybe the most extreme version of reducing the heat transfer coefficient would be to just operate the reactor adiabatically and then to see what happens. So there are a number of things that we could ask here about what if we increase reaction rate, which you could do with a catalyst, which we'll talk about later on in the semester. Is it just as simple as swapping out something, or might we have to take other steps? And so just this problem alone, you can do an exceptional amount of reactor design. So our next derivation involves the final reactor type that we haven't talked about in terms of a non-isothermal reactor, and that's a batch reactor. And of course, we all know that the mass balance for a batch reactor is, dni dt equals Ri times V. Okay. And then there are ways that we can simplify this at the volume's constant, et cetera, to bring in the concentration. But we'll leave it like this for a moment. The important thing when we're talking about non-isothermal operation, of course, is not the mass balance, because the mass balance isn't going to change, but it's the energy balance. And we started with CSTRs and PFRs with the open system energy balance. And of course here, for a batch reactors are closed systems. Semi-batch reactors, of course, are an exception to this, but a true batch reactor is a closed system. And the energy balance for a closed system, right, is that du equals dq plus dw. And in case some of you guys have never seen this notation, the d with the slash means that it's an imperfect differential, because there's no such thing. So when we integrate this, you can think about what delta U might be, but there's no such thing as delta work. That's not a thing, right? When you integrate an imperfect differential like this, you just get work, right, or heat. And that's why it's written that way. Now, there are two different cases that we can think about for a batch reactor. The first one is adiabatic operation, right? And that was the first one that we considered for the flow reactors as well. So of course, adiabatic just means that dq is equal to 0. Now, in reactors, we often don't have shaft work. We often don't have electrical work. So the only type of work we'll typically have is PV work. And so then du is equal to minus PdV. Now, if the pressure of our system is equal to a constant, then we would have du plus PdV. And when the pressure is constant, that's equal to dH, right? Because H is U plus PV. And so when the pressure is constant, that's just the enthalpy, okay? And that, right, would equal 0, right? Because we just brought this to the other side of our equation. Now, what does that mean? Well, if I put this in terms of intensive variables, right, this means that dNH is equal to 0, or that the number of moles times the enthalpy at the end of our process is equal to the product of the number of moles times the enthalpy that is there initially. Now, the way that we've written this so far is that we have multiple components because we have multiple reactants. And so this means that the sum of NiHi at whatever our final temperature is just equals the sum of Ni0 times Hi at our initial temperature. And remember that Ni just equals Ni0 minus the ratio of the stoichiometric coefficients times Na0 times X. And this was the result of essentially the ice tables and the mass balances that we did a few lectures ago. And so we can put that into there. And when we do that, what we find is that we have the sum of Ni0 minus the ratio of these stoichiometric coefficients times Na0 times X times the enthalpy at that final temperature equals the sum of Ni0 times Hi times T0. And we're going to do something that looks very, very familiar because it's very similar to what we did for the flow system, is that we can combine that term with that term, okay? And doing that results in Ni0 times the sum of Hi minus Hi at T0, and that equals the sum of the ratio of the stoichiometric coefficients times Na0 times the conversion times Hi at the final temperature, right? And all I did was combine the two terms I circled, and then I moved that to the other side of the equation, okay? Now, we know some of these already. Remember that this thing is just delta H, right? Which is just the integral of Cp dt, right? And we also know that the ratio of the stoichiometric coefficients times Hi of t, or the sum of those, is just equal to minus delta H per mole of A, right? And that's a substitution that we already made before. And when that's the case, this ends up looking very, very simple. This becomes the sum, which I forgot up there, sorry about that. That becomes the sum of Ni0 times the integral from T0 to T of Cpi dt equals minus Na0 x times delta H of reaction, right? And I can redefine Ni0 as theta I times Na0, just like we did before. And then this equation just becomes the sum of theta I times the integral from T0 to T of Cpi dt equals minus delta H of reaction times the conversion. And of course, once I made this substitution, this Na0 canceled with that one, okay? And the last thing we can do is ask ourselves, well, what would happen if the heat capacities were approximately equal to a constant? Well, then the integral simplifies. And then we get the sum of theta I Cpi times T minus T0 equals minus delta H of reaction. And we can solve this for the temperature, right? So T equals T0 minus delta H of reaction times the conversion divided by the sum of theta I Cpi. And it's worth noting that this is exactly the same expression that we had for an adiabatic flow reactor, whether it was a CSTR or a PFR. So that's good, right? So we end up with the same with the same expression, regardless of the reactor type, if it's an adiabatic reactor. The only complicating factor is if our reactors are not adiabatic. And we've solved that case already for the CSTR and used it earlier in this lecture for the PFR. So now let's do this for the batch reactor as well. Well, in our batch reactor, right, again, we start with du is dq plus dw. And now if we make the same assumption that we only have PV type work and we are operating at approximately constant pressure, well, this just becomes du is dq minus pdv, right? du plus pdv equals dq, and that just means that dh equals dq. And remember, we said this was dnh, even for the adiabatic case, and that this really was the sum of now dnh equals dq. Okay. And now we're interested in the batch reactor, how these things are going to change with time. And of course, dq dt is just equal to q dot, right? It's just our rate of heat transfer out of our reactor. And we already have a definition for that. It's the same one that we used for the open systems, where this was UA times T star minus T. And so we're left with the sum of dnihi dt equals UA times T star minus T. Okay. So our next step here is that we're going to use the product rule, and we know then that that's just the sum over I of Ni dhi dt plus hi times dni dt is equal to UA times T star minus T. And these expressions hopefully look familiar because we also tackled them when we were looking at the PFR. So, of course, dhi just equals Cpi dt, right? So dhi dt, we're going to get a time derivative with respect to the temperature. So that's good. And it's something that we were hoping for. Now, dni dt, we also know this, right? That is just Ri. And How we're going to treat Ri will depend on whether we're talking about one reaction or multiple reactions. So right now, I'm just going to find an expression for a single reaction, and we'll use that in the next lecture. Then in the next lecture, we will also look at multiple reactions and what happens, or how do we utilize this term when there's more than one reaction? Because everything we've done so far tries to get everything in terms of A, right? Right? That's what we would normally use. But what about reactions that don't involve A? They're also endothermic or exothermic. And the example we'll solve next time is A goes to B goes to C. Well, of course, that has one reaction enthalpy, that has another one, but both of them don't involve A. So somehow we have to take both of those into consideration. And we'll do that. So we'll do that next time. We'll do an A-centric problem, and we'll do a problem that has multiple reactions. So for now, though, let's make this substitution, right? So we'll put this one into here, and we'll put this one into here, right? Just like we have one reaction. And if we do that, right, this just becomes the sum of Ni CPi times dt plus the sum of Hi times Ra times the ratio of the stoichiometric coefficients times the volume equals Ua times T star minus T. Well, again, we're going to use this fact that the sum of Hi times the ratio of the stoichiometric coefficients just equals minus delta H of reaction at our temperature of interest. And so if we do that, this becomes the sum of Ni CPi dt over T minus Ra times delta H of reaction times the volume equals Ua times T star minus T. Okay. And if we solve for the change in temperature over time, well, we find that dt equals Ra times delta H of reaction times the volume plus Ua times T star minus T divided by the sum of Ni CPi, which could also be a function of temperature. And that is the result of our energy balance for a batch reactor. And it should look really familiar because it's almost the same as we had for a PFR. There's only two differences, or three differences. One is that instead of volume, here we have time, which makes sense for a batch reactor. Multiplying the reaction rate here, right? We multiply by volume, so that term wasn't there in the PFR equation. And in the PFR equation, this was Fi, not Ni. But unsurprisingly, right, since the math for a PFR and a CSTR are very, very similar, their results from the energy balance are also very, very similar.